Yeah, thank you very much for the introduction, and thank you all for being here. So yeah, exactly. Working the intersection between number theory and cryptography, and today I'm going to talk about supersingular isogeny graphs, modular curves, and Galois representation, which is kind of a very broad title. It basically encompasses the history of number theory in the last 8 years or so. But I'm going to try to look at those objects from a very cryptographical point of view and try to convince you that not only we can use results in number theory to gain information about isogeny graphs and therefore application in cryptography, but we can also work the other way around. So we can use the knowledge that we have and that we acquire through cryptography to gain information about these number theoretical objects like modular curves, modular forms, and Galois representations. Okay, so here is a very brief list of contents. So I'm going to introduce the main object of study, which will be supersingular isogeny graphs. I'm going to talk briefly what happens if we endow supersingular isogeny graphs with some modular structure. So introduce what is a modular structure, what is a modular curve, and what happens to the isogeny graph when we add this extra piece of information. And then I'm going to talk about the method of graph of Mestre and very briefly about Galois representation in the end. Okay, let's start with isogeny graphs. So the main object of study will be elliptic curves. So genus one, smooth projective curves with one distinguished point at infinity. And instead of looking at elliptic curves, which by the way have an amazing structure on it by themselves, we will tend to look at those objects as in relation with the others. And the relationship that we have between elliptic curves are algebraic maps that are called isogenies. So you can think of isogenies as surjective morphisms on the set of points, or as algebraic maps whose kernel is very well known, is in fact a finite subgroup of some order inside the set of points of elliptic curves. And the order of this kernel is what we call the degree of the isogeny. So isogeny graph will be exactly graphs whose set of vertices are isomorphism classes of elliptic curves, which are labeled by their J invariant. And the maps between them, so the edges between these vertices, are isogenies. And we will normally look at isogenies of a very small fixed degree. So you can think of 2 or 3. So here are 2 examples. We're working in characteristic P equal 11. We have 2 J invariants, so 2 isomorphism classes of elliptic curves. On the right, you have the 2 isogeny graph. And on the right, you have the 3 isogeny graph. So one of the reasons why in cryptography we care a lot about these graphs is that they have a very nice regularity. And in fact, you can see that the 2 isogeny graph is a 3 regular, so it's n+1 regular, and the 3 isogeny graph is 4 regular. Okay, so from each vertex you have L+1 outgoing and ingoing isogenies. I'm going to talk about this later in more details, but if you construct this isogeny graph and you look at this adjacency matrices, you can try to compute the characteristic polynomials. So here's the one for the 2 isogeny graph. Here's the one for the 3 isogeny graph. And you can look at the eigenvalues of this characteristic polynomial. You can see that the first 2, so 3 for the 2 isogeny graph and 4 for the 3 isogeny graph, actually gives you the regularity of the graph. So here you have 3 regular and here 4 regular. And again, I'm talking about this later, but the second eigenvalue actually gives information about the traces of Frobenius on this elliptic curve, which turns out to be the modular curve gamma 011 associated to the congruent subgroup gamma 011. Okay, so let's do a step back and introduce all the names and all the terminology. Whenever we talk about elliptic curves over finite fields, so in positive characteristic, we have 2 big families, the ordinary elliptic curves and the supersingular elliptic curves. So there are very different ways of distinguishing between these 2 families, but the way I'm going to look at those is looking at the endomorphism rings of this object. So an ordinary elliptic curve is an elliptic curve whose endomorphism ring is an order in a quadratic imaginary number field. Okay, so it's something commutative. Is something of order 2 over z. And the supersingular case instead has endomorphism ring, which is always a maximal order but this time inside a quaternion algebra. So it's something of degree 4 over Z, and it's something non-commutative. So if we consider, an important thing to say also is that there's a very important theorem that tells us that whenever two elliptic curves are isogynous, so are connected by one of these maps, then their endomorphism algebra has to be the same, which in turn means that ordinary elliptic curves can only be isogynous to ordinary elliptic curves, and supersingular elliptic curves can only be connected to supersingular elliptic curves, which means that when we study isogeny graphs of elliptic curves, we still have this distinction between the ordinary case and the supersingular case. Now, this is what happens in the ordinary case. As we said, ordinary elliptic curves has an endomorphism ring, which is something inside a quadratic number field, is an order inside a quadratic number field. And whenever we have an order in a quadratic number field, we can construct its class group. And it turns out that the class group of this object actually acts on the set of ordinary elliptic curves, and this action is commutative. In turn, this gives the isogeny graph this very nice and rigid structure. And this structure here takes the name of volcano. And the reason is that you always have some sort of crater in the center. So this is sort of the aerial view from the top. You always have a crater in the center, and then you have descending isogeny alongside the volcano. And the reason I'm saying descending is because if you look in the endomorphism rings of these elliptic curves, well, this one is bigger than the other one. And in fact, this one is contained in the one above with index given by the degree of the isogeny. Now, this nice structure and the fact that we have a commutative class group action was exploited in 1997 by Couvang to first propose a cryptographic key exchange protocol based on these isogeny graphs. It was independently rediscovered 10 years later, around 10 years later, by Rostov and Stolbunov, and it works in this way. So we consider a set of ordinary elliptic curves, and we construct the isogeny graph. We construct the isogeny graph relative to, a set of primes. Okay, so in this case, we're not considering just one, but we're considering a small set of primes. And then the two parties publicly agrees on one starting vertex. They choose their secret path, and their secret path is the action of an ideal on this elliptic curve here. So in this case, the secret key is the exponents that the two parties gives to these three primes in the example. And then they compute the action of this product on this elliptic curve. So in this case, 2, 1, minus 1, 2, 1, and then 1 in the negative direction. Alice ends up with EA. Bob's does the same with his secret key, minus 2, 0, 1. So 2, negative 0, and then 1. They publicly exchange the information about the ending vertex. And then Alice, starting from EB, which she received from Bob, reapply her secret key, so 2, 1, minus 1. And Bob, from EA this time, reapplies his secret key, minus 2, 0, 1, and they end up sharing the same secret elliptic curve. And the reason why everything works nicely is because we have a commutative class group action on the set of ordinary elliptic curves. But the fact that we have a commutative class group action, well, on the one hand makes everything works fine, but on the other hand makes this protocol weak. And in fact, in 2010, Childs, Zhao, and Shukarev adapted a quantum algorithm by Kuperberg to propose a quantum attack on this protocol here. So in some sense, having an action makes things look nice, but makes also the protocol vulnerable. So the obvious question is what happens in the supersingular case. Now, the history of supersingular isogeny, the history of the study of supersingular isogeny graph is, again, very old. It started back in the 40s, where Brandt, using the connection between supersingular elliptic curves and quaternion algebra, was studying what happens in the quaternion side, so in the quaternion realm, and was studying not isogeny graph, but graphs of ideals inside quaternion algebras. And 10 years later, Heitler sort of generalized his study to the case of what's nowadays is called high-Claire order, which is just the intersection of two maximal orders in a quaternion algebra. Their goal had nothing to do with cryptography. They were more interested in constructing modular forms, looking at those objects. But in fact, supersingular isogeny graphs are very interesting objects by themselves. And this is the reason why we like them a lot in cryptography. One of the reasons is that we know exactly how many points we have, exactly p over 12, well, roughly p over 12. And even more importantly, we know that everything we need to do or everything we need to compute can be done over fp squared. So over just a quadratic extension of the base field, which is not the case in the ordinary situation. So in particular, every vertex is defined over fp squared, every isogenous can be defined over fp squared, and every endomorphism can be defined over fp squared. Of course, since the endomorphism ring is not anymore an ordinary quadratic algebra, we lack the commutative class group action that made things look and work so easily. But on the other hand, we know that this graph has very nice mixing properties. So when we talk about supersingular isogeny graphs in cryptography, there are two main families of protocols for key exchanges. One is SIDH, which was proposed in 2011 by Luca De Feo and David Zhao. And this is not really an adaptation of Couvagny, Rostos, and Stolbunov in the supersingular case. This is more of a reminiscence of a hash function that was proposed 5 years before by Goren and Lothar. And the way it works is they still construct paths, this time in the supersingular isogeny graph. But this time, instead of exchanging just information about the ending point, they need to share some extra piece of information, which in this case comes in the form of the action of the isogeny on some torsion points. You might know that this protocol, or its most famous instantiation, Psych, was broken less than 2 years ago. And the way it was broken is somehow surprising because we used to believe that every supersingular isogeny-based crypto system had a security based on the difficulty of finding secret path or constructing the endomorphism of supersingular elliptic curves. But these attacks actually show that there are other ways of attacking this kind of crypto system. The way they do it is they embedded the supersingular isogeny graph in some other isogeny graph of higher dimensional abelian surfaces, worked over there, and then reprojected everything down. So somehow these show that supersingular isogeny-based cryptography has to fear even for some different sites. The second family is the family of Seaside, which were proposed in 2018 by a group of people, Castri, Lang, Martin Del Pani, and Renz. And this is more of an adaptation of the picture I showed you before in the ordinary case to the supersingular realm. So the way it works is, well, visually it works exactly the same way as Couvagny, Rostos, and Stolbunov. So you pick a starting point, you make ideals act, and exchange information about the ending point. But the way you can readapt that crystal system in the case of supersingular elliptic curves is you have to restrict your attention to those elliptic curves that are defined over the base field, so over FP. So you have to discard all those elliptic curves that are defined over FP squared. And you also have to look at just those endomorphisms that are defined over FP. So as I said before, all endomorphism ring of supersingular elliptic curves can be defined over, all the endomorphisms of a supersingular elliptic curves can be defined over FP squared. But in order to make this thing work, you have to restrict your attention to those that are defined over FP, over the base field. So in some sense, you're discarding a lot of points in your key space. But in this way, it turns out that you can recover the class group action and you can make things work exactly the same way. So during my PhD, one of the main motivation that I had was to sort of recover the same class group action without the disadvantage of Seaside. So without having to discard like a big bunch of supersingular elliptic curves. And the idea that we had was to, instead of just looking at the endomorphism defined over FP, try to embed a quadratic, an imaginary quadratic order inside the endomorphism ring of a supersingular elliptic curve. So just to be formal, we define a K orientation, where K is a quadratic imaginary field, to be just an embedding of the quadratic number field inside the endomorphism algebra of the supersingular elliptic curve, which is the quaternion algebra ramified at P at infinity, where P is the characteristic of the field you're working on. And if you have an order O defined inside of K, you define an O orientation to be just an embedding of O inside the endomorphism ring. And you say that this orientation here is primitive if basically these two definitions agrees. So if the image of K intersected with the endomorphism ring is isomorphic to the image of O. So in this way, and using this extra piece of information, we can actually recover the volcano structure on the supersingular isogeny graph, and we can recover the class group action, which makes possible to sort of reconstruct a similar picture to Couvent, Rossum, and Stolbuno. So here is an example of what happens if you consider the isogeny graph, the two isogeny graph defining characteristic 71. So this is the classical supersingular isogeny graph, and you endow it with this orientation structure. And here the orientation is given by the Eisenstein integers, so by adding a primitive cube root of unity. So what happens is that you recover volcano. So in this case, we're looking at it from the side. The crater here is just 1 point. Reason being, this order here is class number 1. And the other difference is that this graph here on the left is actually infinite, because unlikely the case for ordinary elliptic curves, you don't have to stop when at some point, because you need the Frobenius endomorphism to be defined, but you can actually go down as much as you want. A consequence of that, of course, is that, sorry, in this graph here, you will see the same J invariant appearing multiple times, meaning that, in fact, the same elliptic curves is oriented, of course, by, well, first of all, different orders, and also by the same orders, but in different ways. And you have to be careful when you construct a cryptographic protocol, because, again, you don't want to build endomorphisms, which means you don't really want to construct loops in the isogeny graphs. And so if you have the same elliptic curves appearing too many times at the same level, there's a high probability of hitting the same elliptic curve when you make your ideal acting. And this is something you want to avoid. Here is just another example. Same characteristics, so 71. But this time, we are orienting everything by the ring of integers of Q square root of minus 79. Again, this is the top view of the volcano. This is a class number 5 order, so the crater would be a dimension 5. And I just highlighted 17 just to show once again that you might have the same elliptic curve appearing multiple times. This doesn't mean that in this graph, these objects are the same. They are the same elliptic curve, but it's oriented in a different way or by a different order. So in this graph, they're not the same object, but when you project it down to the supersingular isogeny graph, they are exactly the same elliptic curve. One of the other advantages that we had imposing this extra structure to the isogeny graph was that, unlikely the case for C-side and SIDH, where you construct isogenies by looking at rational points, so you actually need rational points defined on your elliptic curve, we were able to do all our computation working just with J invariance, so just working with modular invariance, okay? And this was one of the motivation for looking at what happens if we endow this graph with some level structure. Okay, so let me just give you a very short motivation, and then I will explain what this means. So there are actually many different reasons why we were interested in looking at modular structures on supersingular isogeny graph. One is that, once again, when you work with isogeny graph, you always have to consider that each isogeny from one elliptic curve to the other has a dual isogeny going back. And again, since you don't want to construct loops, because this means you're constructing an endomorphism, and this is proven to be equivalent of constructing of finding the secret path, which would break the crypto system. So adding level structure actually gets gets over this problem because somehow it gets rid of the dual isogeny, meaning you don't have to bother about distinguishing the dual isogeny from the others. The second reason is that if you add the right level structure, then you can rigidify the automorphism group of the elliptic curves, which means you will get rid in the supersingular isogeny graph of those special situations like having having two isogenies connecting the same vertex, or having a different number of incoming and outcoming isogenies between the same two vertices. The third reason is a bit technical, but rigidifying the automorphism group might help you shorten the distance you have to walk before you walk down the volcano, before you're able to distinguish between the action of two ideals. So if you look back at the picture I showed you before, since this is a class group 1, if you make one ideal acting at this level, then you will get back on the same elliptic curve. And here again, if you act on level 1 by two ideals, then you will get back to the same elliptic curve. And even here, you might have that the action of a prime sends 48 to 17, but this means that also its inverse will get to 48 to 17. So you're not able to distinguish between the two actions. And the distance you have to walk down the volcano before distinguishing the two actions can be shortened if you add the right level structure. And finally, but probably most importantly, if you add some level structure, the Q modular polynomial, the other polynomial giving you the isogenies, are much, much smaller. Okay, so what does it mean adding level structure? So we have to first define the modular group, which is just the quotient of SL to Z modulo plus or minus 1. SL to Z being the set of 2 by 2 matrices with integral coefficients with determinant 1. You can prove that this group of matrices acts on the upper half plane by this kind of transformation. The upper half plane being the set of complex point with imaginary part bigger than 0. And this action here is very interesting because you know that the upper half plane classifies lattices up to homothethy. And since you have this bijection between lattices and elliptic curves, this means that the upper half plane also classifies elliptic curves up to isomorphisms. So if you're able to study the quotient between, or the quotient of the action of SL to Z on H, then you might find an object really classifying isomorphism classes of elliptic curves. Inside SL to Z, we have some special subgroups, which are the principal congruent subgroups defined by gamma n for some integers n. These are those matrices that reduces to the identity modulo n. You can think of that as quotient, the kernel of the map from SL to Z to SL Z over NZ. And we say that a group gamma, a subgroup gamma of SL to Z, is a congruent subgroup if it contains one of these principal congruent subgroups for some n. And that n is the level of the congruent subgroup. Some special examples are gamma 0 n, which I briefly mentioned before. This is a set of matrices reducing to upper triangular modulo n. And gamma 1 of n, which is set of matrices reducing to, again, upper triangular, but with ones on the diagonal. So I'm not going to spend too much time on this, but it's important to notice that when you consider the quotient of the upper half plane by SL to Z, what you obtain is some kind of object which looks like a sphere with a missing point. You can sort of fill in that missing point by considering the action on the extended upper half plane, which is the union of the upper half complex plane by what we call the CASP, so the projective line over Q. And what happens is if you study the action of SL to Z on this object, you get what we call the complete modular curve over C, which is actually a sphere, a complete sphere. So here's an example. This is the fundamental domain for SL to Z, meaning that in fact every point in the complex upper half plane maps univocally to one and only one points in F. Now, if you took the action of SL2Z on F, then you have to identify these opposing sides. You identify these two arcs of the circle, and then these 2 points here identifies with infinity, and what you obtain is in fact a sphere. So this is a genus 0, and this is the modular curve called X1. Here's an example for gamma 0, 2. Again, genus 0, so I don't remember exactly how you identify this, but you still get a sphere. And this is the fundamental domain for gamma 2, which is again a genus 0. For genus 1, the picture becomes a little bit more complicated. And the most important part, as I was mentioning before, is that in fact these objects have a very nice interpretation in terms of what their points actually classify. So as we said, if you take the action of SL2Z on the upper half plane, this classifies isomorphism classes of elliptic curves. Again, because points on the upper half plane classifies lattices, and you have this bijection with elliptic curves. Now, you may wonder what happens if instead of considering the action of the whole SL2Z, we take one of these congruent subgroups like gamma 0n or gamma 1 of n or whatever. It turns out that gamma 0n, so points on the modular curve attached to gamma 0n, classifies pairs of elliptic curve plus a subgroup. And the order of this subgroup is exactly the n that you have here. So in some sense, points on X0 of n are elliptic curves plus a subgroup of order n, which means that they classifies elliptic curves plus an isogeny, because you can look at that subgroup as the kernel of your isogeny, which in fact means that point on X0n actually classifies isogenies of order n. So from each elliptic curve downstairs, when you lift to X0 of n, you obtain a different number of points, which correspond to all the different isogenies that you have leading from your elliptic curve. And something similar you can do with gamma 1 of n. So if you construct a modular curve associated to gamma 1 of n, you find that the points on that modular curve classifies elliptic curves plus a point of order n, which means that if you construct your curve x1, you lift it to x0 of n, and then you lift again to x1 of n, you're lifting an elliptic curve to all the isogenies that you have. And then for each of the subgroups defining the kernel of the isogeny, you just pick one point as a basis for that subgroup. And this gives you the points on gamma 1 of n. Here's an example of what happens if you endow the supersingular isogeny graph with some, in this case, gamma 0, 3 structure. Okay, so again, here we're working over in characteristic 23, and we're adding gamma 0, 3 structure, meaning that we're adding gamma 0, 3 structure. And as you can see, gamma 0, 3 is not enough to rigidify the whole picture, because we still have some sort of spatial vertex here. You see, we have a different number of isogenies here. But you still get a much bigger picture, and you can still look at this, seeing that you are adding regularity and you're getting rid of this weird situation in between these two vertices. So these 2 points reduces to 0, these 4 reduces to 19, and these 2 actually reduces to 3. So here is an example. Sorry, it's not an example. This is the picture of the modular curves that we're mostly interested in. And I'm going to explain why in a moment. But just to give a name to all these objects, here you have x1, which is just the upper half plane modulo the action of the whole SL2Z. So this curve here classifies isomorphism classes of elliptic curves. So just J invariants. You have x0, 2 here, meaning that each point here is an isogeny of degree 2. And here you have the non-split Cartan modular subgroup. I'm not going to talk about that, but in some sense, if you look at the function field, you're just adding cube roots. Here you have x0, 3. So again, points here classifies isogenies of degree 3. And here you have the whole level 3 structure. This is enough to rigidify the isomorphisms, and I have an example afterwards that shows that. If you compare, if you compose these two, you obtain this modular curve that we call y. And above y lives what we call we decided to call the Weber modular curve, which in fact has a function field generated by one of the three Weber modular functions. And one of the reasons why we were very interested in this modular curve is that it's still genus 0, which means that we have to deal with just one parameter, but it has degree 72 over x1. And as I said before, modular polynomial becomes smaller and smaller the more you climb up the modular tower. So being genus 0, but still having a high degree over x1 means that the modular polynomial that you're going to construct are way smaller than the one that you have to use over x1. So here's an example of what happens to the isogeny graphs when you add that level structure. So here we're working over F7, so characteristic 7. You have only one supersingular elliptic curve. This is the two isogeny graph, meaning you have 3 isogenies going there. If you add gamma 02 structure, then you obtain this object here. If you add non-split Cartan modular 3 level 3 structure, you get this object here. If you add gamma 03 structure, then you're gonna get this graph here. Things becomes a little bit more interesting when you climb up a little bit. So here is the modular curve y in the picture before, so the composition of x02 and the Cartan non-split. So you get this picture here. The nice thing is that you're somehow start losing backtracking. As you can see, this is not a undirected graph anymore. And on this side, with the full gamma 3, the full level 3 structure, then you redefine all the automorphisms, meaning you're losing all the double edges, all the loops, and everything looks quite nice. And finally, if you climb to X, which was the modular curve in the upper right corner, then you get this picture here, where you basically compose the advantages of the two graphs below. So you don't have backtracking isogenies, and you have a rigidified picture. So this is not exactly the Weber modular curve I was talking about, just because it's already big enough for this picture, and I didn't have enough space to put the whole Weber curve, which is of higher degree over x1. Okay, so let's hope. Nope. Okay, sorry, just 1 second. Okay, yeah. So again, this is another example. Here we're working characteristic 61. This is the classical supersingular isogeny graph. This is what happens if you give an orientation to the graph. And this is what happens if, together with the orientation, you add some level structure. And in fact, here we are adding Weber modular structure. So the W modular curve that we had before. So the nice thing is, once again, you're losing backtracking. So once you step down from the crater, let's still call it a crater. When you step down, then you can only go down. You can go up. And again, as I was mentioning before, Weber modular polynomials are quite small. So this is a polynomial that gives you the relations between these invariants here, between S bar or R or 45 and S bar, for example. And as you can see, these are pretty small polynomials. I didn't have an example of the classical modular polynomial. I should have it here, I'm not sure. Yeah, just for a reference, this is the classical modular polynomial of order 2. So as you can see, there's a big difference. Here is the classical polynomial, and here is the Weber polynomial. Okay, so you can see the difference both in the size of the coefficients and in the number of monomials that you have. Okay, so let me just talk about now the method of graphs, and then hopefully everything will come together. So the method of graphs is something relating the word of modular curve and modular polynomials and modular forms to the word of isogeny graphs. It all started in 1941 with the work of Düring, relating, in fact, the isomorphism classes of elliptic curves with with classes of ideals inside quaternion algebras. And again, in the following years, the main object was to study these things in order to get information on the modular forms. And it all came to the 70s, where Eichler was able to prove that, in fact, you can span the whole group of modular forms using this theory, so using the study of isogeny graph and graphs of ideals. And using this theory, Pizer was able to describe an algorithm for computing modular forms. And in the end, in the 80s, Oesterl and Mestre were able to rephrase the whole structure in terms of supersingular isogeny graphs. Okay, so let's have a brief look at what I was talking about. So we have to talk about Brand matrices. These are defined in the following way. So consider a prime and consider the quaternion algebra ramified at that prime at infinity. Just for reference, this means consider a prime. If you look at the elliptic curves in that characteristic, their endomorphism algebra will be exactly this quaternion algebra here. You can fix a maximal order in the quaternion algebra, and you can look at a list of representative of isomorphism classes of left ideals for this order. Again, by the work of Düring, these are in bijection with the isomorphism classes of elliptic curve. So each one of these ideals correspond to one elliptic curve, one isomorphism classes of elliptic curve, of course. And the way it works is that if you construct the right order associated to these ideals, then that order is the exact endomorphism ring of the supersingular elliptic curve. Starting from that set of representative, you can construct the Brand matrix in this way. So you have to count either the number of ideals in that class contained in JI of norm a multiple of JI by n, or you can equivalently count the number of ideals in one class which are contained with index n squared in JI. Or if you want to rephrase the whole thing in terms of quadratic forms, you can count the representation numbers of n by this quadratic form here. Here, Qi and Qj are the norms of the order associated to the ideals Ji and Jj. And once you have a quadratic form, you can construct the theta function associated to it. And it turns out that this theta function here is in fact a modular form for the subgroup gamma 0p. This means that this function behaves well with respect to the action of gamma 0p. Okay. This is again very just a toy example. We're working again over F23, again characteristic 23. You have the quaternion algebra with one maximal order, which is described by that. Here, J is basically square root of -23. You have three ideal classes. If you remember from the graph I showed you before of supersingular isogeny supersingular curves over F23, there were three vertices. You can construct the Brand matrices associated with 2, 3, and 101. So these are the matrices. As you can see, the sum over the column is exactly L plus 1. So in some sense, there's some sort of connection with the regularity of the isogeny graphs. You can construct the normic forms that I was mentioning before. If you construct the theta function associated with these normic forms, then you get a modular form. And you can use the information about this Brand matrix here or the normic function to reconstruct the graph of relations between the ideals in the quaternion algebra. And if you reconstruct this graph using this information, you obtain something that looks exactly like the isogeny graph over F23. So as I was mentioning before, a major step in this theory was the work of Eichler in the 70s. And the main conclusion that he was able to draw was that if you repeat this construction and you reconstruct this theta function associated to these Brand matrices, then what happens is you're able to span the whole set of modular forms associated to gamma 0p. And the way he was doing it was constructing the C vector space with basis, the representative of the classes of ideals. You construct this module and you construct the map going from this module time itself down to the set of modular forms over Q, and you basically associate to each ji and jj the associated theta function. Okay, and using this construction, you're able to span the whole set, meaning that you can reconstruct every modular form associated with gamma 0p. One of the main objects of my work, together with David Cole at the University of Marseille, was to sort of reinterpret the work of Brand, Heikler, and Mestre in the view of what happens if we add some extra level structure to this whole construction. So in order to do that, we really have to go briefly through the construction of Mestre, so it's the method of graphs. It resembles very much the work of Brand, so all the ideas with Brand matrices, and in fact, it's just a translation of that in the terminology of supersingular isogeny curves. So as I said a couple of times, supersingular elliptic curves and ideals in quaternion algebra are in bijection one to the other. So once we have done the construction on the quaternionic side, we can try to translate everything in the supersingular isogeny setting and gain information on the modular curves and on the modular forms using this method here. So this is exactly what Hecke did, constructing the Hecke model. This time, instead of using a basis, which is the ideal classes, we use the vertices of the supersingular isogeny graph. Meaning, in fact, we construct a module which is the free abelian group over the set of isomorphism classes of supersingular elliptic curves. And in this sense, you can reinterpret the adjacency matrices of these isogeny graphs as Hecke operators acting on the set of modular forms. I'm not going to talk much about that, but in fact, this module here can be interpreted as, well, this module here over FP bar can be interpreted as the monodromy group, again over FP bar, of the fiber at P of the neural model of the Jacobian of the modular curve, which actually means that if we're able to study this object here, exactly as I did in the example at the very beginning of the talk, and we're able to study the Hecke operators in terms of adjacency matrix of the supersingular isogeny graph, we're able to gain information not only on this graph here, but also on the set of modular forms and on the modular curve associated to the subgroup. So here is an example. Working over P37, we have 3 supersingular elliptic curves over F37. They have trivial automorphism groups, meaning that we don't really have any special vertex. This is quite a regular graph. This is the matrix associated to the adjacency matrix associated to the 2 isogeny graph. It has this minimal polynomial here. Once again, the eigenvalue 3 gives the regularity of the graph, and the rationality of the 2 other eigenvalues means that, in fact, the Jacobian of this modular curve actually splits as the product of 2 elliptic curves over Q, of course. Yeah. So far, what we have done is we have used the supersingular isogeny graph and the knowledge that we have of the supersingular isogeny graph to gain information on modular forms and modular curves. But in fact, you can actually do the exact opposite. So you can use the information that you have on modular forms in order to gather information about the supersingular isogeny graph. And in fact, this is somehow something that was already possible, but kind of unfeasible. What we plan to do, or we are trying to do now, is we are trying to see what happens if we endow all this construction with some extra modular structure. So what happens is, what happens is, in fact, with the identification of Hecke operators as adjacency matrices of the supersingular isogeny graph, we are actually able to construct isogenies. And this is what Mestre was doing. And in fact, he was able to prove that this was feasible, but the counterpart was that he had to restrict himself to the case of the modular curve x1 or the modular curve x0n for n smaller than 13 and different from 11, because this is a genus 1 modular curve. And so he came up with some count algorithms, some count tools that use this construction to construct isogenies, but the counterpart is this becomes really cumbersome either for small and moderate L. But with the addition of some higher level structure, we are actually able to extend this. So in this slide, I'm just describing how you can reconstruct the Hecke module with, instead of just elliptic curves, but with isomorphism classes of what's called enhanced elliptic curves, so an elliptic curve with some extra structure. And one of the consequences that we are able to draw was in terms of Galois representations. And the fact we were able to show that adding level structure, we are able to somehow construct Galois representation that do not need to be semi-stable. Okay, I'm not going to talk much about that because I'm running out of time, but here is just an example. Here the modular curve is x5, which is of degree 60, and this is the resulting isogeny graph. So you have only 1 point over f2, which splits in 5 different points over f5. And this is the adjacency matrix. And one of the reasons why, if you add some level structure, we are able to, reinterpret the work of Hecke and sort of improve it, is because even if these adjacency matrices are becoming bigger, they're growing with the level, they are very sparse, as you can see from here. So they can still be used in quite an efficient way for our scope. And I think I'm going to stop there. Yeah. Yep. I think you can quantify the reduction on the coefficients. On the number of monomials, this is slightly different because it doesn't depend anymore on the degree of the cover. It actually depends on some symmetries that pops up when you construct a modular curve. So the reduction in monomials the reduction in the coefficients is given by the degree of the cover. But the number of monomials actually depends on the modular curve. So it depends on the situation. It actually depends on the symmetries that you find.